Hey guys, welcome back to Rocket Gyan, my fellow space tubers. And how are you all? I hope you all are doing good. And it's been a long time since we actually met and saw these launches. So how are you all? Hi Louis Smith. Hi Satyanarayan. Hi Benjamin. I'm Mars 2028 and Adam is mildly intelligent. Hello and welcome all. So today we have gathered here to witness another launch, and this one will be the H3 rocket launch, and hopefully this one is not gonna uh, keep us wanting for more. That's what should I say, right? Because previously, if you remember, we were here to witness this launch, but this was cancelled uh, just the very last time, and it happened due to some issues with the engine. And if you remember, so that was a hot fire abort. It was like the engine started, but it did not ignite properly. And initially what we thought that it was because of the SRB3, not those SRBs which are there, which you can see in this screen, are not have not like been ignited. The problem is with the SRBs, they have there is some issue that cause engine SRBs to not ignite. But later on the investigation and uh, you know actual study revealed that the problem was not with the SRB. SRB was working fine as expected. The problem was with the engine. So there is an engine. The start sequence is there in this rocket, in which first of all the computer decides whether the engine is working all good. The engine needs to work all good. It needs to come to full thrust, needs to be working as expected. After that, only and only after that, those computers give command to the SRBs to ignite. If that does not happen, that means there is some issue. So last time also this happened, that the SRB did not even get a command to ignite. So how would they ignite? And because there was some issue with the engine itself. What issue exactly was there? Well, we don't know about that. And if you there are some folks from the Japan, we watching this, so if you know about it, do tell us in the comments, in the chat, so that we all can have some knowledge about it. But right now, as per my knowledge, we don't know the exact reason, but we do know that it was the engine issue. So yes, we are. Hey Wildflower, welcome. Oro Ama, welcome to the stream. Oh, from Argentina. That's great. Yes. Hello, Smith. And we should be good with this rocket launch today, hopefully, and we should not have any hiccup. So, without any further ado, let's just go and see what this rocket is all about. Okay. So if you see this rocket in this image, what do you see? Don't you see that this rocket is bit like squashed into this launch pad? Because it is. So this rocket is slightly bigger than their previous rocket, which was the H2A, and but the vehicle assembly building which they have right now is according to the H2A. So it was built according to the size of the H2A. Now, since the H3 is bigger rocket, how would they accommodate this rocket with this launch pedestal? So for that, what they did was simply they just squashed in the rocket, like literally, like when we pack our luggage and it's just not closing it, we just push it inside, do whatever we can, and then the luggage bag, we close it. Something like that is done here. You can actually see the rocket is inside the launch pedestal, and this is because to fit it inside the VAB for the assembly and then the rollout. So there is that. So this rocket is around capable of 4 tons to sun synchronous orbit, which is great. This will be the heaviest rocket launch, heaviest rocket which Japan has ever built. This should replace the existing H2A. H2A, I think, still has some launches, not so sure. I'll had to see for that, but we are good for the almost like this rocket is doomed to replace the H2A if not already retired. So yes, let's just have a deep look into it now. So this is the two-stage rocket. So we have the boosters attached here, the engine, the first stage here and the second stage here, and then the fairing. So this is a bit thicker rocket. There is also that the H2A was not so thick, but this one is. So, and because of that, let me just, yeah. So these are the configurations which it can fly. I think one of them, most probably the H330S, is not so sure whether it will be like in production or not, but other are will be. So let me just give you a like example of what these numbers mean. So we have H330S. 30S means 3. The first number represents the number of engines in the first stage. So the first stage engine will be 3 on this rocket, thanks to the thicker size of the rocket itself. The diameter is thickened from the previous H2A. And then we have the H322S. So the first number represents the number of engine, second number represents the number of boosters, and the S represents the size of the fairing. So there is S which is short, and then we have the long. So we are having H322S, which you can see, and the H324L. So this is which we have here. So just a second. And today we should be having the H322L, which is actually flying. This one and the H324L, as you know now that the 4 represents the number of boosters, so there will be 4 number of boosters. Okay, so these are the configurations which it can fly, and the maximum capacity that it can carry is around, as I said, 4 tons to sun synchronous orbit, which is great, which is amazing. Now let's have a look at the what should I say, the a little bit of how things are in here. So H332L. Okay, so this is like the one which we don't even see in any of the config, but it will give us the idea of how the things are inside of the rocket and how they are actually stacked up. So we have the engines here. So let's talk about the engines now for a second. So the first stage engine is the LE9 engine, which uses the expander bleed cycle. If you are into rockets and into rocket engines, you will be amazed that yes, they are using an expander bleed cycle for the first stage, and in fact they are the first one to ever introduce an expander bleed cycle into the first stage. And there are some issues why the other companies or orgs all around the world haven't been able to make it, as well as is it even like what should I say, reliable to make it? Is it even why should we invest money in it? Like, there are so many things which I'll talk about. I got you covered, so don't you worry about it. But what you need to know is that this is the world's first expander bleed cycle engine which is being used in the first stage. Okay, so the first stage uses LE9. That is the LE9 engine. It uses liquid oxygen and liquid hydrogen as its fuel, which is evident from this big orange tank. And the second stage is also uses the LE5B3 engine. So the 3 is the third generation of the LE5B, and this also uses the liquid hydrogen and liquid oxygen as its fuel, and then the fairing and obviously the um SRBs. Okay, so let's talk about the LE9 engine. So this is the LE9 engine which you can see in front of you. Okay, so this is, let's talk about like what was the issue with the expander bleed cycle not being used in this first day. So first of all, let's understand the expander bleed cycle itself. So this is the expander bleed cycle. So as the name suggests, expander and then the bleed. Okay, so what happens in this cycle? So in traditional like gas generator cycle, what we have a pre-burner where the gases are mixed and then the it is burned. The name suggests pre-burner is where the gases are burned like previously before it is actually burned into the main combustion chamber, and the exhaust which is generated from that pre-burner is used to run the turbine, which in turn rotates the turbo pump. That is the working of a simple gas generator cycle engine. Okay, now what's difference in this? Different in this is that here you can see there is no pre-burner, so it is much more easier to make, as well as what it actually happens is you can see the fuel is being actually pumped in this heat exchanger, which is nothing but regeneratively cooled nozzle as well as the combustion chamber, and it uses very what should I say in it uses a very wonderful method to actually make use of the existing energy and use that to do some work by just having a phase change of the engine, the fuel. So here it is passed through the heat exchanger, the phase change happen, it turns into gaseous state, and that gases are fed into the turbines, which rotates the turbine, and then obviously this is a bleed. So those after the turbine is rotated, that is just thrown out of the system. So it's an open cycle engine, but it does not have a pre-burner, so it totally and completely relies on the heat exchanger. Remember and focus on this point: totally and completely dependent on the heat exchanger for the phase change. Okay, so this is how this works. Now coming back to this engines in front of you, the LE9. So here you can see, here also what happens, the liquid hydrogen is pumped. You can see here it is going through this turbine which is used to rotate that, and then everything happens which you can see. So the thing is, problem with the expander bleed cycle in the first stage is that, as I said, it totally and completely depends on the heat exchanger to have a phase change, and if the phase change is not what should I say, violent enough, then it won't be able to rotate the turbines. All right, so what happens now, we are having some issue, a chicken and egg problem. If you know, the volume increases, like if the volume increases by 2 times, no, let me just rephrase it. If the length increases by 2 times, the volume increases by 8 times, but the surface area increases by 4 times. Now this is a big bottleneck for the sea level engines, because the heat exchanger is small, the nozzles are small. You don't have a big nozzles like we have for the vacuum engines, right? So the heat exchanger part is really very small, so the phase change does not happen properly, and then if the phase change does not happen, then the engine cannot work because the turbines would not receive those exhaust gases. Okay, so this is the problem with why we don't have the expander bleed cycle in first place as the sea level engines. But somehow Japan always solves the complicated problems, technological problems, and they have solved this also. So we are having an expanded bleed sea level engine now, uh, and not so sure about actual construction, like how did they solve it. We'll shortly read about it, but yeah, this is what they have done, which they are very famous for, solving technological problems with ease. Okay, so yes, this is the problem. As I said, the volume increases 8 times, the surface area increases 4 times, and you need to have a larger surface area to uh, cool your gases, to change the phase of your fuel. And yeah, so this is the thing. Okay, so this is the LE5 engine, which is, you can see this is the second stage engine, and it has a big nozzle, and it can use that big nozzle for the heat exchange and have a proper phase change for the vacuum one, but that is not the case with the sea level. Okay, now this is the generation, like the development cycle. So here we had the LE5, then the H2 uses the LE5A and LE7. H2A uses LE5B2, the second version of LE5B, and then the LE7A, and the H3 finally is using the LE5B, the third generation, and the LE9 for the first stage. Okay, now this is what we have. So this is the aim of this rocket, for high flexibility, high reliability, high cost performance. And one of the reason why this expanded bleed cycle engine was used for the first stage was this high cost performance, because the gas generator cycle are a bit complex to make, and they don't have much what should I say, uh, efficiency, because you are actually losing out on that exhaust gases in the pre-burner, because the pre-burner are not very, stoichiometrically mixed gases. It does not have that, so there is not proper like work which is taken out of the energy which we have. But here that is not the case. It is taking out almost all the energy, but yes, it is also giving some out, but you are not having a pre-burner where you are actually burning the gases in a low stoichiometric ratio, which is causing low efficiency. That is not happening here. So the efficiency increases in this, and also the difficulty to make the engines decreases, because you don't have much moving parts in there. But again, that chicken egg problems arises, but they have solved it, so that's not a problem for them. Now if I talk about the LE9 engine itself, so this is how it looks like, and you can see there, this is the exhaust one, this is the pumps, the exchanger, which you can see here, and yeah, this is how the engine looks like. So these are some of the specifications of the engine. You can see the specific impulse is 422 seconds, which is phenomenal. As compared, you can see the LE7A engine, LE7A, and these efficiency and all. So yeah, this is how the engine looks like. If we go on to the next one, is LE5B3. Okay, so this one also you can see the specifications, 448 seconds of vacuum impulse, which is also great. And if I talk about what is H3 rocket, which we have already talked about, not this one. Yeah, so here it gives us certain, like the capacity. You can see the launch capability to 500 kilometers sun synchronous orbit is 4 tons or more, and GTO is 6.5 tons or more, which is like amazing in compare. If you see its rival, it's like GSLV Mark III of India is like can take up to 4 tons to GTO, and it can take about around 6.5 tons. Although the GSLV Mark III capacity would increase to around this level only once once the development of the SE200 engine is completed. But for now, it is the GSLV Mark III is using it can carry 4 tons to GTO. So it's kind of an heavier rocket in that aspect. And also if you see the SRB of this is a bit different from the S2A1. Thus there is a separation mechanism on this one, the thruster separation mechanism, and also the SRB does not have gimbal in it, unlike what we had for the H2A rocket. So this is one of the important thing which you should know. Okay, so now let's move on to the satellite which it is carrying. So it is carrying the ALOS-3, which is nothing but the advanced land observation satellite known as DAICHI, which is nothing but an earth observation satellite. It is a multispectral sensor earth observation satellite. So the resolution for this one is like 2.5 meter to 0.8 meter at nadir, if it goes for a panchromatic view, which is black and white. So it has a ground resolution of 2.5 meters, but if it goes color multispectral, it has a ground resolution of 3.2 meters, and it will be having a life of around 7 years, and the mass which it today means satellite mass is around 3 tons. This will be a subsynchronous, it is going to a sun synchronous sub-recurrent orbit at around an altitude of around 669 kilometers. There will be a revisit time of 35 days. So this is the image which you can see the difference between the sun synchronous and sub-recurrent orbits. Going to sun synchronous sub-recurrent orbit, so there is actually no difference. So I mean, there is a difference. Like, the difference is satellite go around the earth several times a day, and after a few days it passes through the same area at about the same time. So there is a recurrency which is happening in this special type of orbit. And in sun synchronous orbit, there is you can see the angle between the orbital plane and the sun is kept constant, so that it can always receive the sunlight which it requires. That's why very popular for all the CubeSats and all the earth observations satellites which needs constant solar energy. Okay, let's see if I have the live stream. So I hope you got the
about, or launch vehicle is about. All the launch vehicles essentially have the same function, but right at the top we have a place called fairing, which is a payload fairing, and so the launch vehicle is a kind of a transportation unit to transport the satellites or the explorers located in the payload fairing. Large amount of the thrust is required, and so from here below is essentially the engine and the fuel. Right at bottom of our first stage, I don't know what you can see here. And this is where we have the LE9 engine, and it actually uses the liquid hydrogen and liquid oxygen as a fuel. And we have two of these, and adjacent to that, we have the SRB3, which is a rocket booster using solid fuel, and it generates significant amount of thrust. And the second stage, so up until here is first stage, but this section at the top is the second stage. And hidden here is LE5B3, which is also an engine using liquid fuel. So that is how the launch vehicle is made up. And so this first stage, the engine and the rocket booster, these are utilized first to launch into the space. And the launch vehicle it's not the case that it just goes up in the air when it is ignited, but we go through what we refer to as a launch sequence. So various preparation and procedure are required before we make the launch, and I'd like to give some explanation about that today.
You can see the launch
So if
sequence
you can
has
look,
LE9 ignition and then the SRB3 ignition, right? So if LE9 ignition does not happen properly, then the SRB3 won't happen, which happened actually the previous time which they attempted the launch.
the countdown, and preparation proceeds at 240 seconds before liftoff. The language was lost, but before we enter into this mode, the Launch Control Center, and I'll explain about what this is about later on, but within the Launch Control Center, there is a launch commander, and this launch commander will make a final confirmation, give a permission to move into this mode. And there is kind of an instruction button that he presses to go into the automated countdown sequence. And so various preparation, they proceeds, and the flight mode is switched over, and the system is ready for launch 15 seconds before the liftoff. 6.3 seconds before the liftoff, LE9 engine is ignited, and it takes about 5.9 or 6 seconds for the engine to start up. And so we essentially wait for the engine to become stability, and then the SRB3 is fired up, and that will be followed by the liftoff. And so pressing the instruction button in practice means the start of automatic the countdown sequence with a person physically pressing the button. Yes, so it happens somewhat ahead of the actual liftoff. The sequence proceeds, and after the LE9 engine is ignited, it's just an instantaneous decision that leads to the liftoff. And what happened on the 17th of February is that after the LE9 engine was started up and the phenomenon occurred, and after the startup, these are the detailed procedure on this slide. So on the left is the normal the procedure that takes place for a launch, and what happened on the 17th is shown on the right. So after the LE9 engine is ignited, after confirming that it has stabilized, then the launch vehicle would judge and acknowledge that the conditions are met for the launch, and then provide the approval to ignite SRB3. And there is a safety device, and so this is essentially like releasing this safety mechanism. And then after this safety mechanism, then the ignition signal is sent for a liftoff. But on the 17th of February, the previous occasion, after the LE9 was started up, and gave the approval to ignite SRB3, but there is a vehicle controller, which is an important controller within the vehicle. And within this device, there is a instability in the electricity. And so the launch vehicle considered this to be an anomaly. And so despite the fact that LE9 engine had started up, it sent out a signal to cut off the engine, stopping the sequence. So that is essentially what happened the previous occasion.
Okay, so it was an electrical
and
issue.
So after the approval for Ignite SRB3 to the cut off the LE9 engine, it all took place in 1/10 of a second, so not even a time to blink your eyes. This all occurred when the power supply was cut off from the ground facility to the vehicle, didn't it? That's right. And if you take a look at this photo here, until immediately before the launch, the launch vehicle is linked to the ground facility and the movable launcher, which the launch vehicle is standing on through an electrical system connector. And it's through this connector that electricity and communication is provided to the launch vehicle. Now, with regards to the first stage, it's hidden, so you can't see the connection, but there is a connection beneath the launch vehicle. But for the second stage, if you can look towards the top, you can see a sagging line, and this is what is providing electricity and also communication to a second stage. And just before the liftoff, well, this is the vehicle controller. And this is a orangey type looking device. It's just before the LE9 engine, or just above the LE9 engine. And after LE9 engine is start up, and the ground facility, they actually electrically cut off the power at the launch vehicle. And at the bottom is the ground facility, and the vehicle controller. This is linked, and this line is actually cut off. And immediately this was cut off, then the vehicle controllers, the electrical system became unstable, and there is what is referred to as an integrated circuit switch. And so that switch was actually cut off, a semiconductor switch was cut off, and so it's a malfunction. And when that happens, and there is a battery within the launch vehicle, and towards the right, the engine control unit. And so there is a first stage battery to the engine control unit. So the electricity should have been supplied, but because of the instability in electricity, the switch was turned off. And so the electricity was cut off, and that was considered as an anomaly. And this switch for a power supply should have been on, but it was in the off position. And that was the reason why anomaly was detected, right? That's correct. Now, at that stage, LE9 engine was already active. Now, that wasn't a problem?
I just love
well,
what
this
they
is
did
one
right
feature
now.
of the launch vehicle, but of course there was no problem with engine because there was a backup power source. But not just with the engine, but the launch vehicle adopts a concept of fail-safe. Fail means failure, but irrespective of whatever failure one experiences, the launch vehicle can be stopped safely. That is the concept used for design. So even with one failure, it's not a problem. So a safety designed to prevent secondary damage in a sense, isn't it? That's correct.
Wow, I just
And
love
so the
that they...
countermeasures that we implemented. Yes, I forgot to talk about the countermeasures.
Yeah.
Of course, I said the electrical instability, but why did this occur? When the power was cut off, the electricity becomes unstable, and this is technically referred to as a noise. So the current or voltage sometimes becomes larger or smaller, and that is stability. And this sometimes causes a switch that should not have turned off to turn off. So it's a malfunction. But we've implemented countermeasures to prevent the noise on this occasion. Thank you very much for your explanation. Now, we received many words of support and a lot of big...
I just love that what they did right now. I did not even expect them to do this, and they exceeded my expectation. So yes, we have the answer now, guys. What actually happened there, and this one was a pretty interesting one. The first time I'm hearing like this issue, and we have the rocket in front of you.
At the Takesaki Observatory, and now it's at the launch pad. It's standing there this time.
So the underlying issue was not even with the engine itself. The mechanical parts were working fine. That was the electrical part which was having some issue. So let me just summarize what he said. What he actually said was, when the ground supply electrical supply was cut off, there was some switch which is supposed to change the supply from the ground to the battery. That switch had some malfunction, and because of some voltage issue and all those things which he mentioned, there is some noise and all, had some malfunction. Because of that, the first stage battery was not able to supply the electricity to the engine itself, and the vehicle control unit saw that as a anomaly and then shut down the engine. So this actually happened with the... oh my god, just look at that beauty. Just look at that. One of the most beautiful sites which we have, the launch sites. Wow.
So today we have a maximum 5 meters wind. Not a problem, because the maximum is 20 meters. So there are various standards criteria against which we check. Thank you very much. So weather is a very important condition for launch.
And it's looking good.
So there is the LCC, the Launch Control Center, where various work is done remotely. And we have a camera feed from the LCC. So here the rocket's condition is constantly monitored, and fuel loading and the pre-launch checks are carried out remotely as the final launch preparations are made. The Launch Control Center is located 3 kilometers away from the launch pad. Why do we have to have that distance? Can you explain? As we explained, we use liquid oxygen and liquid hydrogen, which are dangerous. So in order to ensure safety, we say 3 kilometers. So any facility that has people in it has to be placed 3 kilometers away from the launch site. So to ensure safety of the operators, it's located 3 kilometers away. So what kind of work will be done in the Launch Control Center, the LCC? Well, the countdown sequence that I explained earlier, that work will be done mainly here. People sitting here, they are in charge of different parts, and so they're looking and confirming the condition of the rocket. And there is the launch conductor also sitting here. Seems everything is calm there. Yes, they're all sitting there, so it means that everything is good. So I want to explain today's broadcast schedule. So first, the overview of the H3 launch vehicle, the mission of the DAICHI-3 will be provided, and message of support from viewers and companies will be shown. Next, a video summarizing the history of the H3, the flight plan, and the flight sequence will be provided, and the launch is scheduled around 10:37. So today's mission, we have liftoff, and then SRP3 separation, fairing separation, first, second stages separation, and then ALOS-3 separation at the end. So 40 minutes to launch. So let's introduce the H3 launch vehicle. So we did this last time. JAXA and Japanese companies consolidated their efforts to develop this new rocket. So after the launch of the test flight, it will go immediately into the commercial launch service, so launch business. And so private sector, which is Mitsubishi Heavy Industries, they have been taking part in the design process. If you go into business stage, you will be launching not just Japanese satellites, but satellites from the global market. So we have developed this H3 rocket, which can be competitive in the global market. And so I've already explained the structure. So let me talk about the size now. It's 63 meters length, and this one is 57 meters. There are 2 types of fairings. If you use the long version, it's 63. If you use the short version, it's 57. This time it's 57 meters. Diameter 5.2 meters, one size larger than the H2A. It's difficult to image how big it is. If it's at 57 meters, it's about the same size as the Leaning Tower of Pisa. Did you know? Oh, how about in Japan? Well, there's the Oarai Marine Tower. It's about the same height. That's 60 meters. So if you know the tower, you can see how large this is. So if you really look at this, you can actually sense the hugeness of it. It's a solid, big vehicle. So H2A and H2B rocket had the marking of Nippon on the side, but this time with the hope that the people all over the world will use this, it has been changed to Japan. I like the Nippon too, and we see the national team in sports, and I think it's good that we're appealing Japan, and this H2 representing Japan. So we've summarized the H3 rocket and its path to development. Please watch the video.
私たちが携わる宇宙開発は1957年に旧ソビエト連邦現在のロシアが世界初の人工衛星スプートニクを打ち上げて以来60年以上にわたり続いてきました。 宇宙開発の目的は多岐にわたっており、例えば宇宙という未知の領域を研究し、宇宙や惑星の成り立ちや生命誕生の秘密を解き明かす知的探求心の解明が最もイメージしやすいかもしれません。さらに今や当たり前となった天気予報や道案内、自動運転など私たちの生活に欠かせないこれらのサービスの実現には、宇宙開発による技術が使われていることを皆さんはご存知でしょうか。地上の暮らしをより便利にするために生み出された技術が発展を続け、宇宙開発と交わりお互いを高め合う。宇宙開発はもはや私たちの生活になくてはならないものになりつつあります。私たちの暮らしと密接に関わる宇宙開発に欠かせないのが、さまざまなものを宇宙に輸送するロケットです。では世界中にロケットが多く存在する中で、どうして国産のロケットを新たに作る必要があるのでしょうか。それは日本が独自にロケットを持ち続けることで生まれるメリットがたくさんあるからです。例えば先ほどのような私たちの生活を豊かにするサービスを実現するには、日本が適切なタイミングで必要な人工衛星を自在に打ち上げれる環境が重要になります。それには日本独自のロケットが必要不可欠になるのです。 H3 は現在運用中の H2A の後継機として、今後20年間使い続けることを見据えた日本の新しいロケットになります。国内外問わず数多くの人工衛星を定期的に打ち上げることを目指し、H3 を安定して使い続けることが目標となります。そのためには日本だけではなく世界中から選ばれるロケットを目指さなくてはいけません。 H3 は3つの要素、打ち上げたい時に打ち上げられる柔軟性、これまでのロケット開発で培った高信頼性、低価格の実現を目指し、誰もが宇宙空間を活用できる時代を目標に、徹底した利用者目線で使いやすさを追求していきます。2014年のプロジェクト始動から8年、途中にはメインエンジンの技術課題を克服するために2度の開発計画の見直しもありました。開発を主導した岡田正史プロジェクトマネージャーは H3 をこう語ります。
ロケットっていうのは地上のすごく劇的な進化を宇宙から支えるための乗り物だと思うんですよね。H3 ロケットは構想から約10年のロケットです。打ち上げの成功がゴールではなくて、我々はその打ち上げの成功が出発点だと思っているので、早くこのロケットをデビューさせて世界中の方々から使っていただけるようなものにしたいと思っています。
さまざまな困難を乗り越え、ついに完成した H3 ロケット。試験機1号機の打ち上げはすぐそこまで迫っています。新たなるフロンティアへ、未来を背負った H3 が間もなく飛び立ちます。日本の技術で宇宙輸送をリードせよ。H3 ロケットのメインエンジンとして搭載されるのが、今回新たに開発した LE9 になります。これまで日本が培ってきたロケットエンジン技術を集結するとともに、新たな技術にも挑戦し、 H3 が目指す柔軟性、高信頼性、低価格を高いレベルで実現することを目指しました。エンジンの燃料に液体水素、酸化剤に液体酸素を使い、搭載する人工衛星の重さや投入する軌道に合わせて LE9 エンジンを2機ないしは3機を束ねてロケットに装着します。 LE9 は H2A のメインエンジン LE7A と比べ推力が約 1.4 倍にパワーアップしたことで、固体ロケットブースターなしで衛星を打ち上げることが可能となりました。また重い人工衛星を打ち上げる場合には、固体ロケットブースターをつけるなど、従来の H2A や H2B に比べて幅広い打ち上げが可能となります。このパワーの大きいエンジンを安く かつ信頼性を高く実現するため、これまでのロケット開発で得た経験と新しい技術をバランスよく取り入れました。その中でも特徴的なものを3つほど紹介します。まず LE9 で採用するエンジンの燃焼方式は従来のものよりシンプルな仕組みにすることでより高い安全性を実現しました。またエンジン全体の部品点数を減らすことができ、これにより高信頼性と低価格を高いレベルで両立することが可能となります。次に LE9 には 3D プリンターで製造した部品がいくつも使われています。今までロケットエンジンには形が複雑で溶接やボルトを使った部品がたくさんありました。これらを 3D プリンターで一体成形することで大幅な部品点数削減、コスト削減を実現しました。そして電動バルブの採用でいろいろな作動範囲で燃焼することができるようになります。これにより燃焼試験の回数を大幅に削減することができました。このような最新の技術の粋を集めた LE9 エンジンがたどってきた道のりは決して平坦なものではありませんでした。 JAXA では2005年から約10年間技術実証を目的とした LEX エンジンの開発を行い、2014年から LE9 エンジンの開発が本格的に始まったのです。開発の段階ではさまざまな技術面での問題が発生しました。その一つ一つの壁に向き合い、生じた技術的課題を確実に解決するために、そして今後20年使い続けることができるロケットエンジンに仕上げるために2度にわたり試験機1号機の打ち上げ計画を見直しました。
この LE9 エンジンは2002年から研究が始まってですので、ほぼ20年ぐらいの時間をかけて開発してきたエンジンになります。でもこの技術というのは結構厳格で、我々開発陣の願いとか希望といったものというのはなかなか通用しない、思い通りにならないということが結構ありました。ある意味残酷な現実というものを突きつけられているという部分があります。ただ最後ですね、何としてもこの世界初のエンジンを開発させてやるんだという関係者の皆様、これは我々 JAXA だけじゃなくてメーカーの方とか部品のベンダーの方も含めた強い思い、そういったものが実を結んでこのエンジンの完成にこぎつけることができたというふうに思っています。LE9 エンジンの開発担当者として一点の曇りもなく自信を持ってDAICHIロケットの初号機に使えるエンジンを仕上げることができたというのは万感の思いです。
So more than a decade, we took quite a long time to develop the H3 launch vehicle. Kotani-san, you were involved in the concept for H3 launch vehicle. That's right, more than 10 years ago. So in a team to consider a concept, we had a lot of discussion as to what type of launch vehicle we were going to develop. But after it became a project until now, and so Okada project manager and others, they were saying there were a lot of, the ups and downs. And of course, the development procedure was certainly not that easy. So because I know that, and the state today, we're awaiting the launch, is something that is quite a moving situation for me. I feel so happy that we have arrived at this day today, although it's the second time. We are now at 9 minutes past 10, so we have 28 minutes to go before liftoff. And so I'd like to recap the relationship between the launch vehicle and the satellite. Kotani-san, please. Well, as I have explained at the outset, the launch vehicle is a transportation device. It is a transportation device to deliver the satellite on the top. So it's like a delivery service. Well, that is a super fast delivery service, isn't it? Yes, the Daichi will be delivered to the destination in 70 minutes. So it's super fast. But you need to travel at 8 kilometers per second in order to escape the gravity of the Earth. So there is a lot of fuel. In fact, about 90% of the weight is fuel. Did you know? Yes. So essentially, you can tell by the look that it is made of a fuel tank. So the orange portion is the insulator around the fuel tank. And so essentially, the entire launch vehicle is the fuel tank, isn't it? Thank you. So next, could you explain about the types of satellites? Yes, there are many types of satellites. We have the communication satellite, the meteorological satellite, or science satellite. But on this occasion, we'll be launching Earth observation satellite, which is dedicated observing the Earth, detecting the light from the sun. It's like they're taking photography, and also sends out the electric the radio waves, so you have lidars to make various detection. But on this occasion, we'll be sending up the Earth observation satellite. So thank you. And we have a movie to introduce the Daiichi-3 satellite to be launched, and also interview with Mr. Yonisaka, General Manager.
日々変化する大地の表情を捉え、私たちの社会に役立てる大地の目。大地3号は大地の光学ミッションを引き継ぐ地球観測衛星です。大地からさらに大型化、高性能化した光学センサーを搭載しており、大地の観測幅 70km を維持しながら地上分解能をおよそ3倍向上させ 80cm を実現。より鮮明な画像が得られます。大地3号は衛星直下の地表面を日々観測し、データを蓄積し続け、年や季節などによる地表面の変化を捉えます。アーカイブされた観測データは世界の高精度な地理空間情報の整備と更新に貢献します。災害発生時には被災地を迅速に観測、多種多様な災害に対応するために複数の観測モードを有し、衛星直下以外の任意のエリアも観測できます。観測されたデータは速やかに地上へ、被災前後のデータを比較し、建物の倒壊や道路の寸断など詳細な被害状況を把握します。地球を見守る大地の目。大地3号は地球の安全と安心のために、そして豊かな社会のために宇宙へ飛び立ちます。
2015年にプロジェクトが開始してから設計・製造を行ってきて、昨年10月に製造が完了し種子島に運んだというところでございます。大企業から下町の小さな工場までいろいろなところの会社さんが関わっているので、正確な人数は分かりませんけれども、だいたい30社以上の方々が関わっていただいております。まずは皆さんにこの映像を見ていただきたいと思っておりますと同時に、自分もぜひ見てみたいと思っております。
Tani-san, what did you think? Well, the resolution from the first generation to the third generation of Daiichi, there's been significant improvement in resolution. So 80 centimeters of resolution, and which is like the number of pixels on a digital camera. So 80 centimeters, so that's from a space you'll be able to recognize cars. That's the kind of resolution that we're talking about here. And so from Daiichi-1 to Daiichi-3, it's essentially like the TVs are becoming high vision to 4K. I don't know if you can imagine this, but that's the kind of evolution that we're seeing here. That's a great evolution, isn't it? But because the imagery will be based on high resolution, the amount of data is going to be quite significant, so it's going to be an issue to send that to the ground. Yes, the satellite down to the ground station, so there is an antenna.
So the satellite which they are having is a multispectral one, so which means it can view the images not only in the panchromatic way wherein only the black and white will happen. That has a high resolution though of around 0.8 meters or so, 0.8 to 2.5 meters, but in a multispectral, which is a colored one, it has a resolution of 3.2 meters. And Yeah, so this is not only just in the multispectral, it can view in blue, green, red, and near infrared. So it's a very good thing to have. And the mission life is around 7 years. It also uses this, you can see the Lucas, which is the laser utilizing communication system, which is nothing but a system to communicate with the ground, and it uses 1.8 gigabits per second for communication. Actually, optical inter-satellite communication is 1.8 gbps, and then direct transmission K band of 1.8 gbps also there. So you can see this will be like a communication with the help of the satellite, which is already there. So it will be using the laser communication to send this to the satellite, the geostationary one, and then it will be beamed down to the ground station. So this is actually necessary. If you can see, it ensures that there is a data recovery for a longer period of time. Because the relay satellite is in view for almost half of the Earth, but the Japan itself will not be in the view if it will be a direct communication line. So by having a relay satellite, they ensure that they can send the data very quickly, because the visibility and the communication range will be very wide.
So that we watched the VTR about the communication system. What did you think? And so this concept has been around, but using optical communication shows that the technology has evolved. So huge amounts of data, sending that on a timely basis. How does that help our lives is the issue that I want to learn more about. Okay, then let's ask the people involved in data usage of Daiichi-3, how the data is provided, how they're expected to be used. Please watch this video.
PASCO は航空写真測量の会社として創業し、今年10月で70年を迎えますが、今では航空機以外にも人工衛星、車両、ドローン等により得られるセンシングデータから地理空間情報を収集し、社会課題や経営課題に対するソリューションを提供しています。PASCO は地上運用システムの整備、衛星運用、そしてデータ配布事業を JAXA さんの共同事業者として担います。またデータが広く普及するよう利用事例作りを進めてまいります。第3号のデータは地図データの整備、災害対策、スマートシティやスマート農林水産業並びに環境監視等広い分野での利用が期待されております。第3号で観測したデータは見てみるというPASCOのウェブプラットフォームから入手することができます。見てみるでは利用者は関心エリアや観測期間を設定するだけで簡単に衛星データの検索閲覧をすることができ、続いて処理仕様を指定することでオーダーを行うことができます。第3号から得られる高品質で利用用途の広いデータは衛星データ利用の市場をより一層ダイナミックなものへと変貌させていくと確信しており、私たちがその一役を担うことを楽しみにしています。衛星データが多方面で使われるよう JAXA さんやパートナー企業とともに取り組んでまいります。
土砂災害研究部では豪雨や地震、火山噴火などに起因する土砂災害の被害を防止・軽減するため、土砂災害のメカニズムや対策施設の効果的な整備、警戒避難や監視対策などソフト対策に関する研究を行っています。土砂災害は山岳地や丘陵地で発生することが多く、まずどの場所でどのような種類や規模の土砂災害が発生したのかを把握するために第一3号データを使用する予定です。土砂災害分野で特に変わる点としては、やはり災害発生後の初動として重要な被害状況の迅速な把握が可能となることが大きな変化と思っています。 近年では気候変動の影響や大規模地震の切迫性が指摘されており、土砂災害の頻発化や激甚化が懸念されているところです。防災減災国土強靭化は国を挙げて進めており、第一3号の打ち上げが成功して観測を順調に開始し、災害時には大いに活用されることを期待します。
地図の作成や更新のための技術開発を担う部署です。その一環で衛星データを利用し、効率的に地図を更新するための技術開発を行っています。国土地理院が整備している電子国土基本図の更新に第一3号が撮影した画像データを使用する予定です。電子国土基本図はさまざまな地図の基礎となる我が国の基本図で、2021年9月に施行されたデジタル社会形成基本法において、公的基礎情報データベースという正確性や最新性が確保された社会の基盤となるデータベースの一つに位置づけられています。大きく4つのステップがあります。ステップ1は測量用航空機による空中写真撮影。次のステップ2が図鑑、地図を描く工程です。ステップ3が現地調査。最後が編集で、図化したデータに市町村名などの中期に関する情報を加えて作業が完成します。第一3号の解像度は初号機の 2.5 メートルから 0.8 メートルに向上しています。分解能が向上し、判読できる地物が増えることは地図の精度向上に直結します。今回第一3号のシミュレーション画像を25000レベルの電子国土基本図で利用可能か評価したところ、海、河川、湖の縁となる水害線や道路、鉄道、建物、植生、土地利用といった基本的な地物についておおむね問題なく判読可能であることを確認しており、ステップ1に加え電子国土基本図の図鑑にも利用できると期待を寄せています。また第一3号のデータから都市開発などで大きく変化している箇所を自動的に抽出し、電子国土基本図の更新すべきエリアを効率的に選定できるような技術開発にも着手したいと考えています。地図作成に携わる我々にとって待望の打ち上げです。第一3号から国土の様子を捉えた画像が届くのを楽しみにしています。
So many people are looking forward to the data from DAICHI-3, myself included. Now, this time, we solicited messages of support for the H3 launch vehicle and DAICHI-3. They were pasted on the SRB-3. So after the cancellation, we had the recycling, and we returned to the assembly building, and we saw the messages. At the time, there was anxiety and pressure. I'm sure that the operators were faced with such anxiety and pressure, but I think this really encouraged them. And many companies and organizations participating as supporters, and through the website and through events, they have provided messages of support. Thank you so much. We're very thankful. So your messages of support is going to fly into space. So H3 rocket and the ALOS-3 journey to date is now in a video. Please watch.
You can see the actual arrangement. This is the SRB. So unlike for the H2A, this is having a different separation mechanism, a thrusting separation mechanism. So that there is one interesting one, and as well as it does not have gimbal in it. So there's that, and you can see the total. Okay. This is the static fire which happened, and you could see that everything in the mechanical part it was good, and the last time also it would have worked, but unfortunately there was some issues with the electrical system. So kind of a bummer, because the electrical systems, the software systems can be avoided. Mechanicals, okay, things can happen, but yeah, no worries. The rocket is on the pad and nothing has happened. Now she is ready to go to the sun synchronous orbit. So if I didn't talk about where it is going, it's a sun synchronous orbit, 669 kilometers, and that's a sun synchronous subrecurrent orbit.
H-2B rockets. The work is almost the same, but it's a very large rocket, and so in terms of the clearance, putting it in a narrow space was quite a difficult task. And this
Hi Daniel, how are you?
vehicle was transported. We were walking alongside it, yes, under the rocket. And the rocket is overwhelming, but the launcher, the movable launcher, I really like it. It's very huge. And the rocket, even before fuel is injected, it's a huge, heavy thing. And so I was impressed by the strength of the dollies. More than 400 tons without fuel. And so the heavier ones, heavier configuration would be 1,500 tons. So that's about 1,000 cars, and the two dollies can lift that. So it's a very powerful thing. And we see that the operators waiting at the launch pad. So as soon as the rocket arrives, they start to connect the piping. And I was watching that, and I thought that was really cool. They're really waiting for the launch vehicle to arrive. And it's a difficult task, and there could be a slight misalignment. And of course, they can connect even with that. And we saw a lot of teamwork there.
So we are T minus 11 minutes left. Everything is looking phenomenal right now. This is the animation, but actually the rocket and the launch view is amazing in Japan. So here you can see this is the maiden, yes, this is the first ever flight. After 1 minute 50 seconds, the SRBs are detached, then the fairings are opened up, which you can see exposing the satellite to space. After that, the first stage and the second stage is detached. The second stage lights up and then goes to its destination, and the first stage is comes down to the earth. So if you are just new here, let me just summarize you that this is the first ever rocket to feature the expander bleed cycle in the first stage engine. And yes, they are, you can see they are looking into the space environment also, so that would be deorbited, the second stage, and burned up in the atmosphere. So yeah, so I was saying that this is the first rocket which is featuring a expender bleed cycle in the first stage, and it's a difficult task to do because in expender bleed cycle you require the nozzle surface area for the phase change from the liquid to the gas, and that gas is used to rotate the turbines. So it's difficult in the first stage because we don't have a larger nozzle, but we do have a lot. I mean, a lot, hell lot of fuel flowing. So even more than what we have in the second stage. So there's that. And other than that, it features an LE9 engine in the first stage. The second stage has LE5B third generation, and this is a bit thicker than the H2A rocket, and it will eventually replace the H2A rocket completely, because this is most cost effective, reliable, and made to make sure it can be remade again and again without any problems, as well as it's made keeping in mind the commercial market. So it's accordingly made, and hopefully I am like 80% confident they will be successful this time, but anything can happen in rockets, you know. So not so sure like what would happen, but I'm like very hopeful, and hopefully this will be a good success. So you can see right now T minus 8 minutes, 3 seconds remaining. Everything is looking good.
打ち上げ8分前です。現在、各艇ともロケット打ち上げの最終作業を行っています。また、警戒区域の安全は確認されています。
It's 8 minutes to launch. All systems are now in their final operations. The restricted area has been vacated and cleared.
8 minutes from the launch, and just look at the launch view. This is amazing. I like how did they even make it at the banks of the river, the ocean? Wouldn't it like slide away? Well, this is Japan, anything can happen, you know.
440
So the velocity of the air, you can not the air, that's the velocity of the rocket. So it's 0 obviously right now. 85 meters is the height.
430
Everything is looking good. T minus 7 minutes, 7 seconds remaining. The range is green. The weather is supporting,
420
and we are good to
安
go.
全系準備完了。
This rocket you
Range
can
safety
see.
system is go.
射場系準備完了。
410
Range system is go.
408 407 406 405 404 403 402 401 400
Okay. So yes, this is looking good right now. We are having the mission announcements, and
380
what, we did have an earthquake, but did it happen in Japan?
370
Well, they are better off, you know, if anything is bad is coming up from the ocean itself, they are
打
better
ち
off
上げ
lifting
6分前です。
this rocket.
現在、車上の天候は晴れ。気温摂氏18度。北の風毎秒3メートルです。
It's 6 minutes to launch. The current weather at the launch site is fine. Temperature is 18 degrees Celsius. Wind is 3 meters per second from the north. The weather is still a go, and currently there is no constraint for launch.
本日の打ち上げ予定時刻は
330
日本時間の午前10時37分55秒です。
Today's scheduled liftoff time is 10:37:55 seconds a.m. Japan Standard Time.
Wow, it's happening. Finally, a new rocket. She's standing.
310 309 308 307 306 305 304
She's just standing over there, enjoying the views of this beautiful launch site, and excited for it to go to space.
Is go.
290
Satellites
89
are go.
88 87 86 85 84 84 83 82 81 280 79 78 77 76 75 74 73 72 71 270 69 68 67 66 65 64 63 62 61 260 59 58 57 56
I love this countdown for some reason. Okay, T minus 4 minutes and 10 seconds remaining. Everything is looking good. We can see the rocket will now be topped off with the liquid oxygen, liquid hydrogen, and the vents will be closed.
カウントダウンシーケンス開始。
Automatic countdown sequence has been initiated.
現在、ロケットの管制は滝崎発射管制塔から行われています。
A3 is now operated under the command of Takesaki Launch Control Center.
22 21 220 19 18 17 16 15 14 13 12 11 210 209 208 207 206
2段液体水素地上与圧開始。
Pressurization process of second stage liquid hydrogen has been initiated.
There you go. The vents are closed. They have been topped off. Pressurization is going on right now.
190 89 88
And we are just 3 minutes away from the launch, guys. If you haven't already, give your best wishes to this rocket by hitting that like button. And hopefully this will be another new rocket into the inventory of all the rockets in the world.
Pressurization of first stage liquid oxygen and hydrogen has been initiated.
機体の電源が外部から内部に切り替えられました。
The power has been switched to the internal systems.
Thank you so much, Omar. I try to do it whenever possible, and I try to don't miss any these events. So thank you so much for recognizing. So T minus 2 minutes remaining. Everything is on the spot, ready to go, and I am so excited. That countdown is, yes, it's a bit amusing. And I kind of like that. Under 2 minutes now. Well, this is the second time will be the charm now.
Pressurization of second stage liquid oxygen has been initiated.
Alright, it is happening. See it for the very last time now on the launch pad, hopefully.
打ち上げ1分前です。
1 minute to launch.
Yeah, there you go, ready to launch. T minus 60 remaining. Everything is going good.
Flame deflector cooling is initiated.
Okay, this is happening.
Water curtain 散水開始。
Sound suppression water system at the launch deck is activated.
Silence before a storm. Alright guys, there you go. T minus 20, 19, 18, 17, 16, 15, 14, 13,
Flight mode on.
12, 11, 10.
加工品トーチ点火。
Hydrogen purge igniter on.
全システム準備完
All
了。
systems go for launch.
メインエンジンスタート。
Main engine start.
And liftoff!
SRB3 点火。リフトオフ。
Flight boosters ignition and liftoff.
第一3号を搭載した H3 ロケット天気1号機は2023年3月7日午前10時37分55秒に種子島宇宙センターから打ち上げられました。
We have a successful liftoff for A3 launch vehicle test flight with ALOS-3 from JAXA Tanegashima Space Center at 10:37:55 seconds a.m. on March 7th, 2023, Japan Standard Time.
Wow.
打ち上げ以降、ロケットの管制は滝崎発射管制塔から滝崎総合司令塔に引き継がれています。
The operation control of A3 has been switched from launch control center to
Will it
range
pass the
control
max
center.
Q? Will it pass the max Q?
ロケットは現在東南東方向の太平洋上へ飛行しています。
A3 is flying above Pacific Ocean to the east-southeast.
Going through max Q right now.
打ち上げ後1分が経過しました。
It's 1 minute into flight.
And it has passed the max Q mark, which means structurally it is going fine. Nothing is going wrong. Next up is the SRB separation, which is coming up.
Flight is on course.
And wow, that was indeed a very beautiful rocket. The expansion of the plume is coming up, which you can see. So everything is looking good. We can see the velocity increasing, the altitude increasing. That's what we want. And the pointy end is up and the flamey end is down, right? It's not the other way around. That is scream. That scream is nothing but the ground equipments doing its job. SRBs have been separated. Wow, look at that. Yeah, there you go. Right now they separated.
SRB3 分離
Solid versus separation.
Done
ロ
and
ケットは
dusted.
現在種子島内之浦の地上局から追尾されています
Currently, Tanegashima and Uchinoura ground stations are tracking A3.
That did not look good. That did not look good. Was that good?
第一弾エンジンの燃焼は
I
正
guess
常
everything
乗
was
客
working
高精度
fine.
も正常
The combustion of the first stage engine, altitude control, and trajectory are all nominal.
Ah, there you go. Okay.
ロケットは順調に飛行を続けて
Just
お
a
り
camera angle.
現在の高度は約 84km 秒速約 1.6km
I
です
thought it changed its direction.
The A3 flight is on course.
But-
Current altitude is about 84 kilometers. Velocity is about 1.6 kilometers per second.
But everything is looking good. No, actually, last time also that happened. So that sound which you heard was nothing but some thing which is there in the ground itself. So there is a water separation system and there is something else also which I don't remember right now. But there is something, that sound I know is from the ground itself. So ground supporting equipments itself. So, and we have the fairing separation.
And it is indicated as a line. And the data obtained from the launch vehicle is actually reflected into this. So it's showing the trajectory of the launch vehicle. So the satellite fairing separation has been confirmed. And what you can see is on the screen is X plus, which is the time lapse from the launch.
You can actually see that if it's not the weird 3D projection, that it went towards the eastern direction and then it is going towards the south. So it is actually wasting a lot of fuel by doing that maneuver, but I think that is necessary for it to do.
And towards top left, you can see the altitude and the velocity. So we're traveling at
Again,
more than
if it's not-
200
if it's
kilometers above underground.
Not a weird
50 is,
projection, then yeah, that is what it did.
Per hour. So what that's so it was accelerated to 28,900 kilometers an hour eventually. And so we are almost at the completion of ignition of first stage engine now.
First stage is now completed. It will be separated now.
First stage engines cut off.
And we have separation. Look
First
at
and
that.
second stage separation.
I guess that was animation though, but still. That's dog leg maneuver is also followed in ISRO's launch, but this one was
And so
again
second stage
might be just a
should,
projection, but still.
ignition. But we haven't heard the ignition start announcement as yet. But at ignition at 16 minutes 36 seconds, it will continue to ignite to take the satellite into the orbit.
So the velocity is increasing only. So we have the second engine going in.
So we have seen the launch of the H3 launch vehicle, test flight number 1. So that in itself has, I suppose, made me feel reassured. So we can no longer see it in the sky. So because of the fine weather, that we were able to see it quite high into the sky. We were able to see the B3 separation, but the launch vehicle is a delivery service, so we must separate the satellite. Otherwise, we will not be able to call the entire mission a success. So at this point in time, we still cannot be reassured as yet. And the people in RCC is keeping a close watch on the launch vehicle flight. As we discussed at the RCC, at the tracking stations, it's actually tracking the launch vehicle, obtaining data from it, and obtaining locational information to confirm the current position of the trajectory. So let's confirm the trajectory as was explained, and this is reflecting the current flight data reflected in CG almost on a real-time basis. And what will occur after this is if the second stage is ignited well, then it will be separation of the satellites. So until 16 minutes past the liftoff, we will deliver the satellite to the delivery point. So the elevation
velocity is decreasing, guys. Now,
and
I don't think so. Although you can see that altitude is increasing, that's completely fine, but the velocity one should increase.
The height, but looks like the velocity is coming down. It's coming down less than 10,000 the kilometers an hour. I don't know whether this data is correct or not, but
nah.
It seems that the velocity is coming down.
You can see the trajectory also changing now.
But is this the actual data, or is it based on the system? We need to check.
It's the actual data, that's why.
2段の点火が確認されておりません。引き続き状況を確認中です。
This is an announcement from the Takesaki Range Control Center to all launch operators and personnel. The second stage engine ignition has not been confirmed yet. We continue to confirm the situation.
繰り返します。
Oh God.
現在2段の点火が確認されておりません。引き続き状況を確認中です。
The second stage engine ignition has not been confirmed yet. We continue to confirm the situation.
Well.
So, we have not been able to confirm the ignition of the second stage engine. Well, on this FIP or on this CG, the signal for ignition of stage 2 has not come in, and so the elevation is at 625 kilometers, but the velocity is coming down. But is this the actual situation? We would like to await for updated information. We are confirming the situation right now, and so if you could bear with us. As soon as we receive updated information, we will convey that to you.
Well. So I am like very glad actually that they did not cut off the stream and they showed all the numbers and everything to us. First of all, kudos to them for that. But right now, yes, obviously makes sense now. So what has happened? The engine ignition did not happen. Which one? The second stage. And the difficult part was the first stage. So this was the actually new rocket. See, in my total career of streaming the rocket launches, there hasn't been a single launch, a new rocket launch, and I have streamed so many the first maiden rocket launches. There hasn't been a single maiden launch which has not been gone in a failure or something like that. Although I was confident about this one, because they actually inherited some technologies from the previous rockets, like the LE-5B3, which is the second engine on this rocket, is actually inherited from a very it's like a workhorse for the Japan, that is the H-2A rocket, that itself uses the LE-5B engine. So if I'll show you that thing, the development slide. Yeah, here you can see the S2A and S2B used the LE-5B2 engine, and now they have like the third generation of the LE-5B engine which they are using in the second stage. So yes, the engine was kind of revamped, so it was kind of a new, but the technology, the underlying technology was same. So the main thing was this one, the LE9 engine, which they made completely from the ground up. They tested it, uh, did something which was impossible to do, and that engine performed phenomenally well. Problem is with this, the engine, although it was in my mind, if there was any failure which was supposed to occur, it was supposed to occur at this stage, because was a completely new engine without with no one knowing what's the actual performance would be in the flight, but it did well. This one was already a workhorse, but some changes were made, but still things can happen, right? So yeah, there is that. But what could have happened? Well, we can't say anything. For the second stage, we did not even get some footage.
企画管理主任より打ち上げ作業関係者に連絡します。現在、第2段エンジンの着火が確認されておりません。引き続き状況を確認中です。
This is an announcement from the Takesaki Range Control Center to all launch operators and personnel. The second stage engine ignition has not been confirmed yet. We continue to confirm the situation.
繰り返します。現在、第2段エンジンの着火が確認されておりません。引き続き状況を確認中です。
The second stage engine ignition has not been confirmed yet. We continue to confirm the situation.
Okay. So talking about they should spend 10 to 12K and slap some GoPros on it. Well, the budget is not a problem here. The connection is. Okay, so sometimes what happens during these maiden launches, you don't have that onboard camera views, because you prioritize your data bandwidth to the actual data, telemetry data which is coming down, and you don't have enough bandwidth to accommodate the video signals. So sometimes because of that, you prioritize data over the video, and you don't get the video.
So as was announced, ignition of the second stage has not been confirmed. The situation is being checked and confirmed. To repeat, second stage ignition has not been confirmed, so the situation is being confirmed. From where we are, we cannot see, so all we can do is wait for information to come in. But we're watching the CG and we're talking over it. The separation of first and second stage, we were seeing that the signal was sent, but the second stage ignition start, we did not hear.
ロケットは
Give us a minute.
ミッションを達成する見込みがないとの判断から指令破壊信号を送信しました。
今放送が入ってます。ちょっとお待ちください。
A destruct command has been transmitted to A3 because there was no possibility of achieving the mission. We are confirming the situation.
繰り返します。ロケットはミッションを達成する見込みがないとの判断から指令破壊信号を送信しました。
A destruct command has been transmitted to A3 because there was no possibility of achieving the mission. We are confirming the situation.
Okay, so the self-destruct command was initiated and transmitted, sorry, and now if anyone would be watching it, they would have watched a beautiful, good explosion there. But talking about why did they transmit this thing, this command, was because they, first of all, they did not have any possibility of the second stage to start now, and then it was going, what should I say, in the not so safe area, out of
企画管理
range.
主任より打ち上げ作業関係者に連絡します。状況については分かり次第打ち上げ関係者に別途連絡いたします。これをもちまして本日の H3 ロケット試験機1号機の打ち上げ実況放送を終了します。
The status of A3 launch vehicle number 1 will be announced to all launch operators as soon as it will be confirmed. We are ending today's launch status report.
繰り返します。状況については 分かり次第打ち上げ関係者に別途連絡いたします。これをもちまして本日の H3 ロケット試験機1号機の打ち上げ実況放送を終了します。
The status of H3 launch vehicle number 1 will be announced to all launch operators as soon as it will be confirmed. We are ending today's launch status report.
Okay.
大丈夫です。はい、今放送が入り
As was just announced,
ロケットはミッションを成功する
rocket could not complete its mission, so destruct command was sent. It was decided that the rocket could not complete its mission, so destruct command was sent. Destruct command is we send the signal, and there is this device that is activated to destruct the rocket. And then it will not fly any further and it will come back down to Earth. So we were watching in the CG. The first stage combustion was completed, and we could see that command was sent to separate the first and second stage. 5 minutes 27 seconds. The second stage engine was started to ignite, but in the CG, that signal was not received. We were not able to confirm that. So what happened there? Something that we have to investigate, looking at all the data. So during this broadcast, it will probably be difficult to explain in detail all the phenomena. So please, we'd like to communicate to you through the website or through other media. So we cannot expect more news to come in. And so we would like to conclude the live broadcast for the H3 first test flight. Very regrettable this happened. It's a test vehicle, so there were various challenges. And there were some risks, of course, because it was newly developed. So going forward, we're going to investigate the cause. Yes, we need to identify the cause and then reflect it in the next test vehicle. That would be our mission. So as for the detailed information, please visit the JAXA website. Information will be provided there. Thank you for watching the live broadcast. Thank you very much.
Wow. Okay. Yeah. I was like 80% confident today that this will be successful, although I did not expected it to fail at the second stage level, but actually we have seen so many launches fail at the second stage because in space, in vacuum, you can test the conditions, you can simulate the space conditions in here, but the testing a second stage in a vacuum conditions and simulate the space condition is really very hard, and almost like if you can even simulate it, it's not like 100%. So the second stage problems kind of make sense when you look at this way, because you don't have a proper testing ground to actually test your rockets in the space conditions. So real space conditions are real space conditions. So there's that, and like the good thing is, the positive thing is that the newly developed engine, the first stage, the LE9, was successful. It did its job as it was expected to do. And should we put F's in the chat? Yes, Mars 2028. You all can now, because obviously it's put F's is for the respect we need to give it for the rocket. Well, it was a beautiful liftoff, phenomenal and magnificent and glorious. I just don't have any words, but the liftoff was truly great. And we did see some good views, like how the rocket lifted off, and then tilted to perform the gravity turn, but everything at first it looked like we had some problem with the the, the, the the first stage itself. Because of some camera angle, I thought that was the issue, but no, everything was looking good for the first stage. But then it happened. Then we got to know that after the separation, actually the animation, the thing which you saw about the separation also was just an animation. So maybe it was confirmed, maybe it was not. We still not don't know. But what the broadcaster said, that the command was sent, the stage separation happened successfully, and the command was sent to ignite the second stage, but it did not receive for some reason. Like, what can be the reason, what cannot be, we'll have to wait and see. But if I talk about any other updates, if we have anything, well, we don't, because for some reason the JAXA's launch is not talked about on Twitter, at least. So no, then after that they waited for the second stage to ignite for some time. Maybe they'll but that does not happen, you know. If the ignition does not take place in the first place, it does not happen in the second place also. But it can, like, if the command was itself was not received by the second stage, if that was a connection issue, obviously they can no, it's not like the anyone from the mission control center pushes some button to for it to ignite. So it's all in the internal circuitry of the rocket. See the vibrations and the sounds and all those g forces which the rocket has to handle during the liftoff also is kind of very, very, very destructive. So I'm not I'm not commenting on like what could have happened, but there are certain possibilities, like um uh we have seen the second stage when not igniting, like in GSLV Mark III, which is a very similar rocket to this in terms of category, not in terms of engines and all. But in the GSLV Mark III, when this Mark II, sorry, not the Mark III, Mark II, when the second stage, some similar thing happened, the second stage did not ignite. We got to see that there was some pressure drop in the almost like 50 millibar pressure drop in the tank, which caused the engine to not ignite at that point of time. So there are so many variables which can go wrong during a rocket ignition as well as the rocket flight. But there is only one thing which can go right, and every time it needs to go right for a rocket launch to be success. So this time it did not happen, and they waited if something can happen, but it did not. So after that, they issued the self-destruct command, which was necessary, because otherwise it could have caused some issues when it re-entered the atmosphere, and then caused some created some havoc. It was going out of range, or if it was still in the that range, but you don't want your fully fueled rocket to just re-enter the atmosphere, and then you don't have any control over it. So it's better to just destruct it in space itself. But there is some problem with that also, like the debris which it created now was created in space, and it was at around 600 kilometers altitude. Might obviously most, like almost all of it will come back. That's not a problem because it did not achieve orbital velocity. But destruction is like which you can't totally control. So there might be some bits and pieces which could have achieved orbital velocity. Not so sure, but can happen. So it will depend on like the forces which are there. But nevertheless, at the end of the day, um, it was a good work from JAXA, and this is supposed to be their workhorse. So, and it was only just a maiden launch. So, it is always expected in the maiden launch to something to go wrong. That is what. See, I'll give this title of maiden launch being success when I see that one happening front of my eyes during the live stream, because I haven't seen any of them. There is some issue or the other which is created, and as simple as SSLV, which I was so confident that it will be a successful rocket launch, because it did not have any liquid fuel engine. It was all solid. Only this last stage was a liquid one, but the first launch of that was also not successful. Then the second launch came, and it was a successful one. So hopefully that same pattern would be repeated by the JAXA also. The next H3 launch, whenever that happened, it was supposed to, there was like numerous H3 launches scheduled for this year, but now the flight would be grounded. They will be checking like what happened, countermeasures will be applied, and then the things would go uh, as they should be. So that first flight of GSLV understood the parallel of the history. Yes, the first flight of the Mark II, as well as after that also, there is in recent years, I think last year only, there was a GSLV Mark II failure, which was very unexpected, but it did happen. And then that is what I was talking about, 50 millibar pressure issue. So thank you so much for joining in. I hope you liked it. If you did, give it a thumbs up, guys. And if you haven't already, please subscribe to this channel. I try to bring all the streams and give you the knowledge as much as possible, so that you all can understand the rockets in a very easier way. And it's not like whenever it should be like, the rocket science is not hard for you all, guys. Okay. So now which one is the next? So yes, there is one inaugural launch coming up, I guess tomorrow itself, for another maiden launch of new rocket. Not tomorrow, day after tomorrow. That will be the Terrain rocket, and it will be from Terrain 1 rocket. Relativity Space will be launching it, and that is going to be an interesting mission. That is again a maiden launch of the Terran 1 rocket. Let's see whether this rocket be able to launch, and I'm not so sure about the launch, but let's hope if it is able to go and make it to the orbit in its first launch attempt. Well, that is about to be seen. And yes, I'll stream this launch, so don't worry about it. So yeah, thank you so much for tuning in, guys. I hope you like the stream. If you want to support me in what I do, please consider becoming a member of this channel, or a Patreon link is down in the description. And until then, this is Priyanshu Rohila. You just saw Rocket Gyan. Stay safe, stay healthy, and bye-bye.